For this lecture, what I want to do is spend a little time explaining how you would use Markov chains in a sort of computational setting. So the first thing I'm going to do this progressively from scratch to show you that it's not very difficult. So I'm going to start at least, I don't know how much time I will take, but by the way, this is something new. I'm trying the green screen of death, well, no, the green screen altogether in my back, which is showing, allowing me to sort of hover above the text, and so I don't know what this will be like, but I'll give it a shot in continuing my testing different methods. This will be another one. Okay, so what I want to do is I want to develop things in front of you to show you that what we're doing is not very complicated. So I'm going to include the library iGraph because it's going to be useful. And the thing that I'm going to start doing first is, oops, sorry, when I want to go to the next line, I'm going to enter this matrix that we have here. And so I'm going to call it P, and I'm going to say that it's a matrix. So it has entries 1/2, 1/2, 0, 1/4, 1/2, 1/4, 0, 1/2, 1/2. I entered it. It has 3 rows, and it is entered by a row. Okay, so if I check what the value of P is, I should get the matrix that I want. So as a reminder, so first of all, I'll point out, so if you want to take powers of matrices easily, you would use the package XM, which allows to compute what's called the exponential of a matrix, but it also allows to use the powers of a matrix. And so here, for instance, well, this matrix has 2 zeros, so we don't know yet that it's indeed regular. If you go back to the definition, we know that a matrix is regular if a Markov chain is regular, so if the matrix that's associated, the transition matrix, is primitive. And to check primitivity, I want to show that all entries are positive for some power of the matrix. So we saw already that the second power of this matrix is indeed primitive, and let's check it. Oops. And indeed, you can see that the second power of P is a positive matrix. All its entries are positive. Where was I? Okay, so the first question is, what does this matrix converge to? And if you remember, we saw that what we wanted is the left eigenvector corresponding to the eigenvalue 1. So if we want to compute this, let me just check quickly. Yes, okay, this is looking good. So if I want to compute the eigenvalues of P, let me point out, this is not what I want. This, you will notice, this first eigenvector that you see there is the one that has only ones. Of course, here it doesn't have only ones, but if you look at it, all entries are equal. And I could just make all of them equal to 1, because I could scale that vector up and down to make it equal to 1. And it corresponds indeed to the eigenvalue 1. But what I want is the left eigenvector. And remember that I said that an easy way to compute left eigenvectors is actually to compute the eigenvector of the transpose of the matrix, which is what I'm going to do now. So I'm going to say that EV is equal to this. And now if I look at the components of EV, I get, yes, the eigenvalue 1, and then 2 other eigenvalues. But remember that what I'm looking for is the eigenvalue corresponding to, the eigenvector corresponding to the eigenvalue 1, which is that first eigenvalue here, eigenvector here. But I want it to be normalized, okay, because I want a probability vector. So if I do eigenvalue vectors of 1, I get, sorry, it should be comma 1. This is the eigenvector. Here it's showing, well, actually, in this case, we're looking at a row vector, so it's good. What I want to do is I want to divide this by the sum of, I want the sum of these entries to be 1. So I am going to divide this by the sum of the same quantity. And I find exactly the value that's announced here on the left. I find 1/4, 1/2, and 1/4. Okay. So this is it for this one. Now, what else can we do about this? And before I move on to absorbing chains, let me point out that there are 2 ways to use chains, whether they are absorbing or regular. Whether they are regular or absorbing. I mean, absorbing being the second type of chain we're going to look at today. We can, this computation that you just saw here, it is done so that the, what do we call it? It is giving you the probability distribution to be in the different states. But if you remember the way we talked about the Markov chain, we were looking at this graph, for instance, and what I was describing to you is the way each experiment would look like. And if instead of wondering what in distribution things will do, I am thinking about what happens if I'm actually tracking the experiments, well, I can use this. And let me show you how. So remember, so this matrix is row matrix, it's row stochastic, okay? And the way we define the chain is as indicated here. Where is it? Here. Okay, I'm missing. Yes, here. So what I can do is I can start with a probability vector, and let me make a new thing here. I just need to check at what point I start to overlay myself on the other thing. So let me not call it, or maybe I'll call it little p. This is not necessarily very clever. And recall that one of the things I pointed out is that when you're looking at the evolution, you can start by assigning probabilities at random in p, or random. So for example, okay, let me start with this. I could start and say that P is the vector that has 1/3, 1/3, 1/3. Okay. If I now consider P dot P, so we'll have to check, I don't know if it's going to consider Yes, it is considered that way. P dot P here is just taking that initial state. And so if what it says is that if we start out and there's a probability 1/3 of being in one of those states, like dominant, hybrid, or recessive, then the next step, I have a probability 1/4 to be in the first state, which is dominant. I have a probability 1/2 of being in hybrid, and a probability 1/4 of being recessive. Okay, and if I continue like this, I am going to see how things keep on happening. So I could multiply by the second power of P, and let's actually do it that way. If I multiply by the second power of P, I'm going to get this. And just a remark, we've already converged here. And so we're not going to change. Okay, if I take the third power of P, again, I'm not going to change. So let's start with a different vector. Let's say that we have most of the weight in, so I'm going to say 1/10, 1/10, and 8/10, 4/5 here. So if I do this, then the first iteration says my probability of being in the dominant is 0.075. My probability of being hybrid is 0.5, and my probability of being in a recessive state is 0.425. And if I take the second power, I'm probably going to converge very quickly. But no, I haven't converged yet. Not yet. So this one is actually taking longer. You can see as we raise the powers, we're going to progressively approach the limiting probability, which is 1/4, 1/2, and 1/4. We're almost there. It's going to take some time. So at the 7th generation, I'm almost there. 8th generation. Okay, it's taking some time, but you see that we're progressively converging there. And let's say if I wait 20 time steps, I've almost converged. If I take 50, I have converged to the limiting distribution. But I can also think about using this method to simulate the evolution of a chain. So if instead of starting with a vector that has a distribution of weights, I start with a vector that has this probability 1 of being in state 1, which is capital G, and probability 0 of being in the others. Then when I look at the first iteration of the chain, this gives me the probability that if I started out in capital G, I am in one of those states there. So the way we can think about this is that I can then consider this vector and say, well, if I am just considering one experiment and that I'm picking one individual each time, this is giving me the probability, this vector here is giving me the probability that this individual will be in one of those three states. Okay? So what is happening here is that I could look at it this way and say, well, if I want to see how things evolve, I could then say, well, if I have this probability of being in these three states, I could pick at random one of those three based on what their probability is and say that this is my next state. And if that's the case, then P would not be this probability vector that we have, a little p here that we have here, I would say, depending on which state I have picked, this is where I am now in my second iteration with probability 1. And so, for instance, if here you see the largest probability is 0.5. So suppose I am now in 0.5, then this means that the next time around, what I'm looking at is this. And when I compute this one, I see that I have a probability 1/4, 1/5, and this. But that doesn't mean that I'm necessarily staying there, okay? Again, I can repeat the same process and say, well, if that individual that I've picked has probability 1/2 of being hybrid and a probability 1/4 of being either dominant or recessive, then this is what could happen next time. So let's make a function for this. And I'll try to make it up a bit. This is a little silly. Maybe I'll do it here. Okay. So I'm going to make a function that's going to repeat this process several times. And I'll probably make a mistake, but like I've said before, illustrating mistakes are illustrative of what you can learn from the process, and so I think it's good. So we're going to make a function, so let's call it a Markov chain. It's going to be a function of, I'm going to give it an initial vector, p, which is going to be where I start at. I'm going to give it a transition matrix, capital P, and I'm going to give it a number of iterations, let's say, number of steps. Okay, what do I want to do? I want to say that, well, first of all, so what is my return going to be? It's going to be the state of the system at time t. I'm going to assume that time 0 is when I start. So I am going to make, let's call it out. And in out, what do I need to put? Well, I just need to put p. Okay, and just for convenience, let's actually make what? Let's make out also include the number of steps. Okay, the step number. So I'm going to say that out is this, and I'm going to say that out is a data frame. And that, what do I want to do? I want to say that this data frame has column names, just because it's going to be easy. The first one I'm going to say, so out is equal to C of, let's call it T for time, or it could be a step, let's say step. Okay, and then I'm going to say this is G little g, and G little g, and I'm going to return this result. This way I'll test things as we go. So let's evaluate this, and what am I going to do? I'm going to do that MC of what I called it P, little capital P, and doesn't matter, we take, or actually, so let's say that by default I'm going to do, let's say 50 iterations, okay? So we don't need to give this information. What am I saying? So error in names, value of names attribute 4 must be the same length as the vector. Okay, let's do it like this. Let's say that out is a matrix that has this data and has NR equals 1, so only one row, and we are running by row. Okay, let's see if this works. Okay, so that is the P that I chose here. Let's say that instead of this, we are starting with this, and let's try here. Okay, so indeed, my step is going to be just the step, and this is going to be, it's going to have a 1 in the state that is occupied by the chain at step, whatever step I'm looking at, and zeros for the other states. And so what I need to do now, so this is set up, let's put it's this, now let's say run, and return result. So the run is what? I'm going to say, I'm going to make a temp vector. And that temp is simply going to be what? It's the product that I was taking here. So it's out of the last row of out. Okay, at this point I've only got 1, but I'm going to say out of dim of out of 1. That's the last row of out. And of course, I don't want to take time into that first column that I added, so I just go from 2 to 4. So this is temp. This is the vector that I get, and then I just need to multiply this, by matrix P. That is giving me the equivalent of this vector that I have at the bottom. Okay, so this is simply this here. What do I need to do now? Well, I need to determine where among these 3 positions I am going to go. And how can I do that? There's several ways to do this, but I can simply take, for instance, so if I take, let's call it a prob or probability, and I'm going to say this is RUnif of 1, and that's just it. And just for illustration, what is RUnif of 1? RUnif is the uniform distribution by default between 0 and 1, which is actually what we want here. Otherwise, you would use min and max to specify different values. And what it's doing here, it's taking a random value between 0 and 1 and returning this value. And so what I can say then is, well, where should I go the next time around? So I have this probability vector here, which is going to be the same as this one, because that's what I started with. Okay, so I'm going to have 0, 5, 0, 5, 1. Well, one thing that I could do is if I take the cumulative sum of this, I'm going to get that the probability is going to give you the cumulative probability of things. So here, for example, I'm taking a number between 0 and 1. It is larger than this first entry. And if you remember, okay, so I should do both cumulative sum and this. You will see that what's happening. So I've taken this random number here, 0.8, roughly. So 0.8 is larger than this first entry. And if I look at the cumulative sum, it's between here and here. Okay. So all I need to do is find where this number RUnif of 1 fits in this cumulative distribution. If it is less than the first entry, then it means we have gotten here. If it is less than the cumulative sum of the first and second entry, it means we've gone to a second position. And the third entry, in this case, because we've got 3 entries, is always going to be 1. So if it is not smaller than this or smaller than this, then it is smaller than the last entry, and that means the third choice is the one we picked. So I have this probability, And what I want to do is I want to find which let's see, let's call it prob. Just going to use the same thing, and this is what I would recommend doing. So when you're coding, you just want to, oops, I want to show prob. You just want to see what's happening. Okay, do things on the side. If you were working in our studio, you would have the console and you would work there. Here, think about doing the same thing. I'm going to get rid of everything that I don't need in this thing here. So I want to know which of the cumulative sum terms is, so what do I want to say? So this is always, you'll see, it'll take me a while to get it. Greater than or equal to prob. What did I say? Forgot consum. Okay. So they're all 1, 2, 3. Oh, actually, maybe let me show you first like this. So this is just okay. So those 3 entries are bigger, therefore the first entry is true. Let me try another prob. Okay, I will need to try a few. Okay, so this one should be false, true, and true. So if I say which, and so if I take the minimum, or if I take the first value, actually. Okay, so this means that I have chosen the second position. So this looks okay. So I'm going to say that the index, which is going to be where am I going next, the index is equal to which. So remember we computed this this number already, which of the cumulative sum of temp is greater than or equal to the probability. So this is going to, and yes, and I want the first probability, and I want the first of those entries. The only thing here is that index is relative to temp, which has only 3 entries, and when I'm assigning the result, well, actually, let's do it this way. I'm going to say that temp, therefore, so now I've chosen my entry, which is going to be equal to 1. Okay, I've got my index, so I'm just going to say that temp is equal to, what do I want to do? I'll say, I'll do it stupidly. There's much easier ways to do, well, much prettier ways to do it. I can say that just temp is this, and temp of the index, whoops, is equal to 1. Okay. So here I've selected in my vector temp the entry that is going to get the weight 1. The others are going to get a weight 0. And now all I need to do, and by the way, I should, of course, this is going to be for I in 1, 2 number steps. Okay, because I need to repeat this. For I is number is in here, okay. And yes, of course, I will need to close this parentheses here. So now what I need to do is I need to say that out, I'm going to add to it. So it's R bind to put a new row below the existing ones. And I'm going to put the matrix that we already have. And then what am I going to add? I'm going to make a vector row that is going to have, well, first of all, we need the index of the time step in which we are, and then we need the new temp. Let's see if this works. So to test it on a small case, I'm just going to say that the number of steps is 5. This works, we'll be very lucky. Dimension of out 1 requires, okay, what is happening here? Temp, yes, no, wait, I'm taking dim of out of 1, so that should be good. Temp of this, okay, so let's unroll. So let's take I equals to 1. Let's make this matrix. Okay, so it is worth always unrolling the code, and this is not very obvious when you're using a notebook, but never mind. So here I'm going to make the temp. Okay, so that's where things are not happening. So let's see, do I get to this point? Yes, I do. So if I don't get to this point, so I'm saying temp is, oh, okay, so first of all, I could say, what is its problem? Out requires numeric complex. Oh, yes, I know what's going to happen. Let's just, okay, let's see if I say as vector, this might be what's happening. No, as numeric. Okay, so what is temp now? Okay, looks okay. That's what we want for the first iteration, right? That's what we had behind. Okay, so here I need to say that this is numeric. Okay, so I've run the function. Let's look at this. What? Did the function not evaluate? Okay. I don't want to make this too long, so let me take 2 minutes off while I find my error. Okay. The mistake was ridiculous. You will note that I have moved the parentheses here that I had put here, here. And with this, so let me get rid of this because this was the testing phase. With this, you will see that what we have is the type of thing that we want to see. So in rows, you get the time step. Time step 0 is the initial time step, and that's where I'm giving it the vector 1, 0, 0. Then on the first time step, the chain has remained in the same place. On the second time step, it has moved to capital G, little g. Then it's moved back here. Then it's moved here, and so on and so forth. And so you could do, let's do 20 of those, and you will see that, and it's not the same thing we saw last time. Okay, this time we changed here, we stayed here a few times, we moved here, there, here, 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 etc. You could plot this. So for instance, I could say, okay, let me save this as a result. What do I need to do? Let's save as a result. And what could I do? So let's look at and see. If I wanted to plot the position, I could say, for instance, well, that's easy. So I can make a vector, let's call it V, in which what I'm going to do is I'm going to take MC of GG and multiply it by 1, and add to that MC of G little g and multiply it by 2, and add to that MC of G little g, no, little g, sorry, and multiply it by 3. Because since those entries are, there's only one that's true, what's going to happen is when I do this, if I'm in state 1, then that V will, for a given row, will take the value 1. If I'm in state 2, it will take the value 2, and if I'm in state 3, it will take the value 3. So let's do this, and let's just also put V, so just to check. So here I'm in state 1, then I switch to state 2, then I switch to state 1, then 2, then 3. Yes, okay, so that's working. And so now we can simply plot. Let me remove these. I can plot MC, so I want the step, and V. And maybe let's make it, and of course every time I plot it, it runs a new Markov chain, so I'm not seeing the same thing. Okay, and let me make this so that we can see. So this is, I could label them. I'm not going to do so, but I could. Or maybe let's be precise. Let's say that X lab is time, step, and Y lab is position, state. And what I could say is that there is no Y-axis, but that I'm going to add an axis. So 1 is below, here is 2. And then I'm going to say at 1, 2, 3, and the label is going to be GG, G little g, and little g. And that's it. So you can see this is the Markov chain evolving, where every time, remember, this is important, every time I'm picking a single individual in there. So this is telling me when I pick up a new individual from my box, let's say, what's the type of individual that I get. And I could change the initial distribution vector, of course. I can make a vector here and say, well, what happens if I start, instead of starting in capital G, as I do every time here, let's start as a hybrid. So if I get a hybrid to start with, this is what's happening in this particular instance, but if I run it again, it's going to be different. You see here I stay hybrid 3 times, and then I go here, and then etc. Okay. So this I can delete, and I can delete. Okay. So the last thing I want to go over quickly is what happens with an absorbing Markov chain. So of course we're going to get the same type of thing as before. So if we have an absorbing chain, where was this absorbing chain? So here now I'm going to take a matrix P and let me be lazy. Let me copy it here. So that one has probability 1 here, probability 0 here. Whoops, that is not what I wanted to do. Did that break everything? No. Probability 0 here, and then 1/2, 1/2. So this is 0.5 here, and this is 0. I should probably try not to be in the way. Am I in the way? No, I'm not in the way. And the last row is 0, 1, 0. Okay, well, just out of curiosity, so remember that what happens here is that we are going to be absorbed, and let me do the computation, or maybe let me do this B here, and I'll do the same thing as I did before. So remember, this is an absorbing chain, and if I start, this one is absorbing in capital G, capital G. So I don't want to start here, because otherwise I will remain there. And okay, let's check first. I have not changed at all. I started in the absorbing state. I remained in the absorbing state. What happens now if I start in the recessive state? So here I was unlucky. I went directly, well, not directly. I went to the hybrid state. I followed here and made it into GG, and the next step I was absorbed. Sometimes this is going to be a bit longer. Yeah, for instance, here I've remained in GG a little bit, but in the end, I always end up being absorbed. Just to illustrate things, let me suppose, and this is not this example anymore, let me suppose that I added an arrow from capital G, from the hybrid into the recessive. Then what would that mean in terms of the probabilities here? Well, I can go from from here into, well, let's say that we have still a probability 1/2 of doing this, but that we have a probability 0.25, like a fourth of moving here and a fourth of moving back into capital, into the recessive state. This is, again, I'll stress, this is not the real case, okay? This has nothing to do with the example we're looking at here. So if we do this, then you see that we can indeed return back to the recessive state, but then at some point we get absorbed and nothing else happens. Here, well, this goes on for quite some time. I'm actually going back and forth between the hybrid state and the recessive state. But then finally, at some point, I make the transition into the absorbing state. And from that point onward, there is no more change. Now, let's say that I wanted to do, that's the last thing I'm going to do. Let's see if I can do this in a few minutes. What if I wanted to make a matrix like this? So let's say that we have B here. Let's say that N is the number of states here, and I'm going to, just for the principle, I'm going to say 10. So how do I make this matrix? Actually, that's a good question. I am going to say that P is a matrix that has n rows and n columns, so it's a matrix of zeros, okay? And what is happening there? So I'm going to say that P of 1, 1, oops, is equal to 1, okay? This is the loop on 1. P of nn is equal to 1. And then what am I going to say? I'm going to say that the probability of staying in the same state, I'm going to do exactly like we had before. I'm going to say that the probability, so for I in 2 to n minus 1, the probability of staying there is going to be 1/2. And what else? The probability of going from I to I minus 1 is a fourth, and the probability of going from I to I plus 1, I'm not sure this is going to work. Once again, we'll need to check this, 0.25. And just let's look at P. Okay, so P is a matrix that has 1, 1 and n equal to 0. It has 0.5 on the diagonal, and it has the probability 0.25 each time of moving to the off-diagonal entries. This looks good. So this is the same chain as we have on the left, but with 10 states instead of 4. And let's now do the same thing as we were doing before. And oh yes, the only thing is here, instead of, maybe I should, oops, of course it's not happy. Because my initial distribution vector is going to be, I'm going to put 0 n times, and then I'm going to choose that, for instance, let's say we start near the middle, 5. Here, 5 equals 1. So this is what we want, not between square brackets. Okay, this is going to be messy, so MC, does this use, let me just check. Okay, so this is not good. Setup matrix P, call names, let's take this out. We don't care about the column names here. This should be from 2 to the dimension of out, the second dimension of out. This is a repetition of 0 dimension of out 2 times. We take that the temp of this is here. This tentatively could work. It's going to run into problems, so let me comment out these, because for now those are not going to be this one. Let's see if this runs. MC. Okay, so we started out in 5, which is the 6th index, because remember that maybe we can say that just a function could actually say call names just of out of 1 is step. Okay, so this way we at least have a step that is well named. The others we will see. So we start out in 5, we move to 6, 6, yeah, okay, so just let me continue renaming things. We are going to call them step, and then I'm going to say that I'm going to say what state person D, and this is 1 to length of P minus 1. This is should work. This should work. Let's see if this works. So the number of items is not a replacement. Oh, I've got made something stupid in here. Yes. I forgot to remove the fact that it's the last entry. Yes. Okay, so step and state. State, we start out in state, did I say 4? That was 5 here. This is a little weird. Okay, I don't know what state 0. It started from 0. Why am I? Yes, because, okay. Okay, so now this should work. I'm about at my time. step 1, I start at 5, then I'm at 5, then here, and you can see I get almost to the absorbing state, and then I come back in, and so this chain here has not been absorbed. I could, how would I make this vector? The cat is trying to escape the room. So maybe what I could say is that V is equal to, oh, maybe let's start with V equals a vector that has only zeros. So how am I going to do? I'm going to repeat 0 how many times? 20 times. Okay, because I have 20 time steps. Let's make the time steps a variable. So I'm going to make time steps here. And time steps here. And what I'm going to do is I'm going to go for I in 1 to n. I am just going to say that V is equal to I times MC of, and I want the whole column, and the column that I want is I plus 1. Tentatively, this should work. Let's see what V is. Nah, this is not what... Okay, it's I times... Oh, no, this is MC, so I'm taking... Actually, if I plot MC, it would be easier to see what we're looking at. So this should be 1 times the I plus 1 column. Yes, V equals V plus this result, of course. Okay. I am not finding it, and I'm seeing that the time is running out. Maybe as an exercise, although there's not much time for doing exercises left, but as an exercise, you could try fixing this. It's going to be a very easy fix, and I'll post a updated version of this where this works. But what you want to do is you want to give the entries here weight 1, the entries here weight 2, and so on and so forth, so that the value in a given row is just the sum, weighted sum, and that will tell you whether you're in state 1 or 2, etc. at that point.